Thank you very much. It's a lot of fun to be here. I know lots of the young people here. It's really great to kind of be with friends. It's awesome. So I'm going to talk about some new directions in the search for dark matter. And here's the bottom line, right? We know the dark matter exists. We know it's a new particle as opposed to being a modification of the law of gravity. And if it's a new particle, pretty much like most other particles we know about, it probably has non-gravitational interactions. And if it has these non-gravitational interactions, it is very important to find them, because that way not only do we learn something about the identity of dark matter, we also learn something about where the dark matter could come from, and it also gives us access to a new sector in physics where the dark matter is a part of. So obviously these are very important questions for particle physics and astrophysics and cosmology. The challenge then is, how do you detect dark matter? And the problem, of course, is that the reason the dark matter is called dark is because it's got weak effects, and thus you need techniques of very high precision to be able to find the dark matter. And this is where things get interesting, because if you look at it, in the last 2 decades or so, there have been impressive developments in the field of precision instrumentation. We can, for example, measure magnetic fields today smaller than a femtotesla or so through squid and atomic magnetometers, and also measure accelerations smaller than 10 to the minus 13 little g, where g is the acceleration due to gravity, through atom and optical interferometers. Obviously, you guys have heard of things like LIGO and LISA Pathfinder, which in fact improve these numbers by a little bit more. And what's interesting is that even though these numbers by themselves are incredibly exciting and interesting, anyone who works in this field does not believe that these numbers are final. They actually expect technological advancements that would change these numbers by maybe a couple of orders of magnitude or so every few years or so. So I would say, even as I've been involved in this field, I've seen these numbers steadily improve over time. So it's just interesting to ask this question. This technology is clearly being developed. It's being developed for a number of other reasons, not just due to particle physics. How can we use these technologies to detect new physics, and in particular the physics of dark matter? What kind of dark matter are we interested in? Well, before we answer that question, let's ask, what do we know about the mass of dark matter? There are all these particle physicists in the world. They should be good for something. What have they figured out about the mass of dark matter? Naively, the dark matter could have a mass, for example, anywhere from the Hubble scale, 10 to the minus 43 GeV, all the way to 10 to the 48 GeV, because above 10 to the 48 GeV, if the dark matter is that big, it will bend light a bit too much. And the Kepler satellite has looked for these things, and we haven't found those. So they're called Macho Searches. And so above 10 to the 48 GeV, it's very hard for 100% of the dark matter to be that heavy. But anywhere above the Hubble scale is a reasonable particle, and it naively could have been dark matter. We know one other thing with the dark matter is that it is actually in the galaxy. So the fact that the dark matter is in the galaxy puts non-trivial limits on its mass. For example, if its mass is, say, below 10 to 100 eV or so, the dark matter cannot be a fermion. And that is because as the mass gets that light, its number density goes up. And if you have a fermion, you can't pack too many fermions together. That's Fermi degeneracy. So below 100 eV, the dark matter cannot be a fermion. That's something we know. For a boson, there is no such problem. You can pack as many bosons as you want in the same mode. But ultimately, as the mass of the boson gets smaller and smaller, its de Broglie wavelength gets very big. Eventually, the de Broglie wavelength of the boson can become larger than the size of the galaxy, at which point it doesn't fit in the galaxy anymore. And that puts another limit on its mass, which is that it has to be higher than 10 to the minus 22 electron volts. That's really all we know about the mass of dark matter. Okay? An enormous range of masses exist out there where dark matter could very reasonably be there. And if you have a friend in particle physics and you decide to buy them some beers, they can write you a well-motivated dark matter model pretty much anywhere in this mass range. Okay? So anything we do beyond this is just a guess on what the dark matter could be and try to see if we can have clever ideas to actually find it. So one very reasonable guess is that the dark matter may be tied to the standard model, the weak scale of 100 GeV, the one other scale that we know about in particle physics. Excuse me. And that, of course, gives rise to the weakly interacting massive particle, or WIMP, dark matter. Okay? And the search for WIMPs is a great thing to do. There are many reasons why the dark matter could have been the WIMP, but we've been looking for it for a long time and haven't found it. So this search for WIMPs is soon to hit something called the solar neutrino floor. okay, that neutrinos from the sun are soon going to be detectable in WIMP detectors, and is then a question to ask, how do you search for dark matter below the range when solar neutrinos are going to come and hit it? How do you do that? What techniques do you have to think about? And in addition to WIMPs, as I said, theorists can come up with a lot of models. There's a wide variety of generic dark matter models, okay? I'll mostly focus on things called axions, massive vector bosons. I may not really speak much about dark blobs. I just call them large composite states of dark matter. But, as I said, there's a lot of particles that can fit out there. And the real question to ask is, how do you sensibly make progress over this vast mass range? And today I'm basically going to focus on technologies and ideas to search for dark matter from about 10 to the minus 22 eV in mass, an inverse year in frequency, if you will, all the way to the WIMPs. And also talk about ideas on how to go beyond the solar neutrino floor for WIMP dark matter. So this is the outline for the rest of my talk. I will first give you a very, very brief theory overview. This theory overview is mostly focused on asking what are the interesting, very, very light dark matter candidates that are worth looking for, like axions and massive vector bosons, 10 to the minus 22 eV to maybe about 10 eV or so. And then I'll discuss several experiments. The first is to search for a particle called an axion with a fancy nuclear magnetic resonator style idea. Then to look for something called a dark photon with a fancy radio. Search for certain kinds of scalar bosons with accelerometers. And then I'll discuss two ideas. One is to do the directional detection of dark matter. This is to help us go beyond the WIMP beyond the solar neutrino floor for WIMP dark matter. And also discuss a much more recent work called a magnetic bubble chamber. I'll tell you what these things are. So let's start off by discussing bosonic dark matter, okay? The very, very light bosons. How should you think about them? So before we talk about bosonic light dark matter, let's just understand the boson we know and love, the photon. So this picture shows photons coming out of, some laser. And you can think of these photons as individual particles going out. But an equally valid way of thinking about those photons is to say that the photons are described by a classical electromagnetic field. The field has a non-zero amplitude. When there's a non-zero amplitude, there is going to be an energy density associated with it. And one way to detect that photon is by measuring the time-varying electromagnetic field associated with it. So you can have an antenna, and you can watch the antenna being driven up and down by the photon, like a radio or something. And that's one way to find that. So just like a photon has a classical field associated with it, a dark boson, okay, because it's a boson, will also have a classical field associated with it. So for example, if you have a scalar particle, let's call it the axion, it can have a classical field associated with it. And as long as the field has a non-zero amplitude, it will have a non-zero energy density, just like how a non-zero amplitude gives rise to a non-zero energy density for the photon. So the way these things can be dark matter is that in the very early universe, the Almighty just gave this field an initial amplitude, right? He's free to do that. And that's it. So when the universe started, there was some dark matter. The Almighty said, let there be dark matter. So when that happens, there is going to be a non-zero energy density, and we can show that this energy density behaves a lot like dark matter today. The big difference between the classical field of the photon and the dark matter is that the dark matter is a massive particle, so it's allowed to have very low momentum. In particular, its velocity can be basically zero. And thus, if you look at the classical field associated with it, its oscillations are entirely in the time domain, as opposed to an electromagnetic field where there are obviously oscillations in time and space because momentum is equal to energy. So the way you think about how these particles are produced in the early universe is just that. The Almighty said there's a non-zero amplitude for the field, and thus everywhere throughout the universe, there is this classical field that's oscillating back and forth at a frequency equal to its mass, and that's the dark matter. We don't, of course, live in the early universe. We live today. So even though the classical field started off as being dead constant in the entire universe when it started off, it doesn't remain that way. Today, the gravitational potential of the dark matter has evolved. It's fallen into the galaxy. It's developed a whole bunch of bumps and wiggles everywhere. And you would think of this as a random field, right? The galaxies, that a bunch of things happen to it. And even though this is a random field, you can still talk about some kind of two-point function. You can ask about a correlation length, which is the statement that if I basically have one value of the dark matter field here, how far do I have to go before the field value changes by order 1? Okay? If you think about that problem in momentum space for a second, you realize that the length that you have to go before the field value changes by order 1 is its de Broglie wavelength 1 over mv, like e to the I kx, right? You have to travel a distance order 1 over k to see a change in x, in the field value. And so the correlation length of the field is thus 1 over mv, the mass of the particle times the velocity. And if you're going to sit out there and try to measure this field, what you care about is not the correlation length. What you care about is how long you have to sit and measure that field. So the question then you're asking is that there is a correlation length for this field that is of length 1 over mv. The Earth is moving through this dark matter velocity, this dark matter cloud, also with a velocity v. Thus the amount of time it takes for you to traverse this distance is basically 1 over mv squared. Okay? So what we would call the coherence time, which is basically how long the field changes in a sensible way before it becomes dramatically different, is 1 over mv squared. And this is where things get very interesting. Because if you think about the kind of scalar bosons I'm going to discuss, axions, vector bosons, all these things can come from very, very high energy physics. You know, QCD, scales about the gut scale, and all these kinds of things. Even though they come from ultra high energy physics, the masses of these particles turn out to be pretty small. So a particle like an axion, for example, could have a mass that is order of megahertz. And since the velocity of dark matter in the galaxy today is 10 to the minus 3, the coherence time of the field is 1 second. Which is interesting, because human beings can build experiments that last 1 second, allowing us to measure things. And these frequencies at which things are oscillating are like megahertz frequencies, which are again frequencies where human beings are able to build experiments. Right? So for whatever bizarre reason, it doesn't have to be true, it turns out that these scales can be human scales where human beings can build experiments to measure these effects. Okay? So the main idea here is that just like how I can detect a photon by measuring the time-varying electromagnetic field associated with it, like in an antenna, I can try to detect, for example, the scalar particle, the axion, by looking for the time-varying effects of the field associated with it. That's the main idea. And you can basically see that there's a natural possibility of a resonance here, which is that the coherence time of the field is 1 over v squared times longer than the period, which is 1 over m. And since v is about 10 to the minus 3, you expect a coherence factor of about 1,000,000. So if I have a resonator that is good with a Q of 10 to the 6, okay, then I should be able to just sit out there and measure this field. Now, what kinds of particles are actually interesting? Okay, a reasonable thing to do is to say, well, I'm looking at some very, very light particles, incredibly small mass. So perhaps there is some kind of a symmetry reason why these particles are that light. You might say there is some kind of technical naturalness reason why these particles should be light. And the moment you utter the word symmetry, the ways in which these particles can talk to the standard model are very limited. I would argue there are only 7 possible ways in which these particles can talk to us, even though naively the mass is a huge range, right? But even though there's a huge range of masses, there are only about 7 main operators by which these particles can dominantly talk to us. So if the particle has spin 0, the example would be an axion or some ultra-weakly coupled particle. They appear in many theories of physics. There are only 4 ways in which such a particle can talk to us and still be naturally light. Okay? It can talk to us through electromagnetism, through this coupling A over F, FF dual. Okay? Coupled to QCD, through this operator A over F, GG dual. It can couple the spin of nuclei and electrons through the operator d mu A, n bar, gamma mu, gamma phi n. And couple the Higgs boson through this coupling G phi Higgs squared. Okay? These are the 4 dominant ways a light boson can talk to us and still be light. And just for nomenclature, if a particle couples to GG dual, that guy gets a name. He's called the QCD axion. Okay? It solves some strong CP problem, and there's some baggage that comes with it. But in general, the particle doesn't have to couple to QCD. It could just couple to the other things, and it's still worthwhile looking for. Okay? But we want to look for all of these things. The other possibility is that the particle is spin 1. If it is spin 1, then if it has to be light, okay, have a very low mass, technically what you want is you're looking for what are called anomaly-free couplings of a vector boson to the standard model. And that again restricts what these couplings can be. Once again, the vector boson, which is denoted by F prime here. So we're talking about a new gauge boson, not the photon, it's a new gauge boson. It has its own gauge field. So there's an F prime, and that guy can couple to nuclear spins through a dipole moment. So just like how the neutron and the proton have electric and magnetic dipoles under the electromagnetism, I guess they only have magnetic dipoles, sorry. It's possible that the nucleon, for example, can also have a dipole moment under the new gauge boson. It's a possibility. It can couple electromagnetism to this coupling epsilon F prime F, where F is electromagnetism and F prime is a new gauge sector. And finally, standard model particles could be directly charged under this new gauge boson, and that gives you this coupling G A prime, whatever here. And the only possible anomaly-free current that you can have in the standard model is what is called the B minus L gauge boson. Okay? So these are all the possible operators by which a light boson can naturally talk to us. So what do you do? Okay, if the dark matter is any of these particles, how would you look for it? It's very simple. You take each of these operators, you stick in the fact that these if this is the dark matter, there's an oscillating field associated with it, and that oscillating field will give rise to time dependence in every one of these operators, and you've got to come up with a good experiment to go and search for that time dependence. And in terms of the frequency of these effects, it can be anywhere from 10 to the minus 22 eV, which is 10 to the minus 7 hertz, to something like a gigahertz or so. Now, so far, okay, I would say prior to my work maybe, that the only of these things that we were searching for were axions at a frequency of around a gigahertz or so through this ADMX experiment. ADMX is a terrific experiment. They should be fully supported. It's wonderful. But I would say, given that we know so little about dark matter, and here are all the other possible effects, and a very, very wide range of frequencies out there, let's explore them all. Okay? So the first part of the talk will focus on how to search for all these effects. Now, at this point, if you're a skeptical experimentalist, you could be like, who cares about something like technical naturalness? Naturalness, after all, looks like some sort of story that theorists tell themselves to keep themselves occupied. We live in a world where the cosmological constant is anomalously small, the weak scale is anomalously small, so who gives a damn about technical naturalness? Why should I only look for these effects? That's a very reasonable attitude to take. But what's exciting is that even though there are these 7 possible operators, and it's all motivated by naturalness, experimentally, the number of effects you can look for is much smaller. So as an experimentalist, you can be like, go away, theorist, okay? Tell me what can I go and observe in the lab. So you can ask a very simple question. What can the dark matter field do? Okay? What can the dark matter do? And it's basically this following question. The dark matter is assumed to be a classical field if it is this light. And I'm simply asking, how can a classical field interact with a standard model and give rise to observational effects? Okay? That's what we have. We have a dark matter field everywhere. It's oscillating up and down, just like how a time-varying electromagnetic field. And it can give rise to those only 4 possible measurable effects. The first thing it can do, it can drive a current in a circuit. Okay? Things do that. The other thing it can do is basically it can cause spins to rotate. The dark matter field can exert forces on objects. And it can also change the values of fundamental constants, like the mass of the electron, the charge of the electron. These are pretty much the only possible ways in which a classical field can change something with a standard model. If it's the first of these 2 cases, notice that a small current can create a small magnetic field, and a rotation of a spin will also change magnetic fields, because spins carry magnetic fields. So both of these effects can be looked for with these squid magnetometers or any atomic magnetometer, these very precise magnetometers. And forces exerted on materials can be measured with very good accelerometers. And when you change fundamental constants, you'll also affect atomic clocks and things of that sort, because they are looking at the mass of the electron when they're telling you how the clock beats. Okay? So what you notice is that experimentally, even if you ignore all the theory, these are the 4 possible ways a light dark matter classical field can talk to us. And there are very, very good technological tools available today to go after these effects. Okay? So this makes it possible for you to suddenly look at a very broad class of dark matter with a relatively narrow set of technical tools. And what makes the search interesting is the fact that you're looking for something very specific. You're looking for a time-varying effect, okay? And that is very useful in combating systematics and things of that sort. And you're also looking for a signal that's very narrow bandwidth, right? It's at a very specific frequency, and it has a resonance of 10 to the 6. So it's a very narrow signal in the frequency space, and that is something that should help you beat a lot of technical background. Okay, that's the hope anyway. So let me discuss the 3 experiments that sort of are focused on this philosophy. So the first is an experiment called CASPER, Cosmic Axion Spin Precession Experiment. This one is a pretty well-funded activity. As you can see, all these people who have been foolish enough to give us money. And it's being basically built by Dmitry Budker at the university, at the Johannes Gutenberg University in Mainz and UC Berkeley, as well as Alex Surshkov, who's building it at Boston University. So here's the main idea of CASPER. Let's just look at a neutron, okay, and just think about a general axion, not the QCD axion, just some axion that couples to nuclei. It couples to a neutron, for example, and it couples to this operator, okay, d mu a, n bar, gamma mu, gamma phi then. So if I look at that particular operator and write that down in a non-relativistic limit, you will find that this operator is of the form velocity dot the spin of the nucleus. That's what this thing becomes if you go through your quantum field theory exercise. And what it basically means is the fact that if you keep this nucleon, and the dark matter is going to go through it, because of this velocity and this interaction, the nuclear spin will start precessing. Because this is a lot like a magnetic field dot on the spin of the nucleus style effect, right? So we know what spins do in a magnetic field, they rotate. Similarly, if this effect exists, as the dark matter goes through a spin, the spin will start rotating. It will be random, but it will be coherent over that period. Okay. So what you're searching for these experiments is that you're searching for the spin precession, okay, over this coherence time of the thing. And essentially, if you put in the numbers for how weak of an effect you're looking at, you're essentially looking at sub-femtotesla fields, but things that I've talked about are just in the anvil of being measurable. Okay. Similarly, if you have a vector boson and the nucleon has a dipole moment under it, as that vector boson goes through, the spin will also start precessing because there's a time-varying magnetic field of that vector boson talking to you. For the QCD axion, there's another interesting effect. So you take a neutron, and let's say you couple it to QCD to the operator A over F GG dual. This operator does something very interesting. Due to the anomalies of QCD, it turns out that this operator creates a small electric dipole moment for nuclei. Okay, this is in fact in some version of the strong CP problem. It creates a small charge separation in the nuclei, and the only direction it can point to is along the nuclear spin. Okay, so the QCD axion induces a tiny electric dipole moment for the neutron and the proton, and this dipole moment, of course, is along the nuclear spin. And very importantly, while it's very small, it's oscillating. It oscillates at a frequency equal to the mass of the axion. And so if you apply an electric field, that nucleus will start precessing. That nuclear spin will start precessing, and you could try to measure it. So the basic idea of Casper is that if you can measure the rotation of these spins, you can detect the axion. And here's how we hope to do it. We take a sample of material, we align all the spins in some direction, we apply an external magnetic field, okay, and then we let the axion do its thing. So if the axion has this velocity coupling, as the axion goes through the system, the spins will start precessing. For a electric dipole moment effect, we just use something like a ferroelectric, where there is an intrinsic electric field in the system itself that will again cause the spin to precess. And as the spins precess, we stick a very precise magnetometer next to it to look for the time-varying magnetic field associated with it. You can see that there is a natural possibility of a resonance here, which is that when I set the external value of the magnetic field so that the Larmor precession frequency of the system is equal to the mass of the axion, there will be a resonant response, just like NMR. Of course, we don't know what the mass of the axion really is. So the way we practically do the experiment is that you pick one value of the magnetic field, see if you got a big response, you tune it a little bit, you change the magnetic field, the Larmor precession frequency changes, and then you see if there's another place where there's a resonance or not, right? So we just keep tuning the magnetic field to scan over the various possible Larmor precession frequencies, trying to see if there's an axion anywhere in where we are scanning. Yeah, so that's an important question. So essentially, this sample will typically take to be about 10 centimeter cube or something. So you want to make sure the magnetic field doesn't vary by more than 1 part in a million over that. So you have to, and you know, there are these spin echo style techniques that people try to do to remove that. Oh, it is. That it is. Because if you look at the correlation length, it is 1 over mv, and that is like for these frequencies is basically kilometers. Yeah. You're certainly right that when you go to gigahertz frequencies, that stops being true. Really above 10 gigahertz, but in these frequencies it's okay. So here is kind of where we think we can do with this experiment if everything goes to plan. So these are current bounds on, so this is for not the QCD axion, this is for any axion that couples like this, d mu a, n bar, gamma mu, gamma 5n. These are the current bounds on these things, and this is the axion mass and frequency in EV here, and frequency in hertz at the top, and here's the coupling. So here are current bounds, and basically the red and the blue lines are where this experiment is able to probe new territory in this game. We don't quite get to the QCD axion with this particular technique when we're looking at the velocity dot spin effect, okay, but we're able to cover a lot of other kinds of axions well beyond any current limit where something could really be out there. For the QCD axion, you have to go to that electric field version of the story, which is also being developed at Boston University, and there we really believe that if you can do some very reasonable technology development It's hard, but not impossible. This phase 2 version of the experiment, we are actually going to be sensitive to the QCD axion. And this is basically the range of QCD axions probed here are QCD axions where the PQ breaking scale, if you know what that is at the Gutt scale and Planck scale. So we're really probing Gutt to Planck scale axions with this experiment, should it work. So this experiment already has current results now. This is our first toy demonstration version saying things are making sense, nothing crazy is going on. So this is basically a version of the NMR experiment which we call Casper-Zulf. Zulf standing for zero to ultra low field magnetic, ultra low frequency field. And that is the sense that we have a system where there is not even a magnetic field. We're just simply putting a bunch of spins out there and seeing how they process and seeing something funny went on. Nothing funny went on. Everything worked according to plan, so they tell me. There was no strange new sources of noise or anything of that sort. But this thing is not very, very sensitive because there is no magnetic field, there's no resonator yet, and we didn't actually even get order 1 nuclear polarization. We just get 10 to the minus 4 standard thermal nuclear polarization. But it's, a couple of years of work. That's the result right now. And we actually will have a paper shortly where we have, in fact, laboratorily demonstrated order 1 nuclear polarization still at low frequencies, and that one will push these limits beyond beyond the supernova bounds. Okay, so that experiment is already working. We will have limits on that shortly. Then I'm going to talk about dark photon detection with something like a radio, and this is being built at Stanford by Kent Irvin. Again, the number of people have given us generous funding to make this happen. So here's the basic idea. We're going to say that dark matter is a dark photon, by which we mean it's just a photon with a mass. So this is the Lagrangian. F is electromagnetism. F prime is a new dark photon. Okay, and the idea of the dark photon is basically that it is just like the photon in that it couples to electromagnetic currents, but all charged particles have a tiny charge under it. Okay, an epsilonic charge under it, and it has a mass. Okay, that's the main difference. Photon with a small mass and suppressed couplings to all charged particles. Okay, how do you find it? Well, the basic idea is that if this is the dark matter, there's going to be an oscillating dark gauge boson everywhere, and the oscillating dark gauge boson will have an oscillating dark electric field, and that dark electric field can drive currents behind an electromagnetic shield. Okay, so that is the idea of the DM radio, or the dark matter radio station experiment. So here's what you do. You have a shield. Inside the shield, you stick inside a fancy LC oscillator, okay, very high Q and things of that sort, with a squid to measure the current. So basically, there's a dark matter field out here. It's oscillating up and down. There's a dark electric field. If you build a good shield, it blocks all electromagnetism. It goes inside, and it drives up this LC resonator. And you try to measure that small current with a squid. Okay. Of course, we don't really know what the frequency of the dark matter radio station is, so we just keep tuning the LC resonator to see if there is some frequency where we hear the dark matter. That's the idea. So here's expected reach for this thing with this kind of parameters. This is the ultra fancy version of it. The main thing to understand in this plot is that we're able to cover a lot of territory out here, right? Everything in the blue region, which is many, many orders of magnitude in frequency, and also quite a bit of orders of magnitude in coupling, can be probed with technology that's already very reasonable. DM radio also has first data now. All this proves is that Kent Irvin is really good at what he does. I have nothing to do with any of these things working. So they have a resonator that works. They see a nice big peak out there. That is not the dark matter. It is just the thermal noise in the system being amplified at the resonant frequency. So this was actually a few months ago. This slide is a little bit out of date. They've already achieved, I believe, Q more than 10,000 now in their system. This is just an old slide. That's all. Anyway, things are happening. Okay. Let me then discuss how one can search for dark matter with accelerometers. So here is basically the quick idea here that other than electromagnetism, we said that the only other possible way in which standard model particles could be directly charged is through something called the B minus L coupling. Okay, that's the only other anomaly-free coupling we have. And the thing about B minus L is that protons, neutrons, electrons, and neutrinos are all charged under it. Okay, this is different from electromagnetism, of course, and that has the feature that electrically neutral atoms will thus be charged under B minus L. Okay. By the net neutron number, because a neutron carries charge under this. So already there are a lot of limits on these things, because you can bring two atoms and try to see there's an extra force between them, since they have a net neutron number, and B minus L will cause them to move towards each other, if should it exist. That already constrains the coupling to be very small, less than 10 to the minus 21. But can we do better if this is a dark matter? We can, because if the B minus L is the gauge boson, this dark matter, there will be an oscillating B minus L gauge boson. That one will have an oscillating electric field associated with it, and that oscillating electric field can directly accelerate atoms because atoms now have charge under B minus L proportional to their net neutron number. So the dark matter can directly exert a force on atoms. Okay? And what's interesting about this force is that this force depends upon the net neutron number of the system, okay? Which means naively, in fact it does, violate the equivalence principle. So normally you would think everything should fall the same way or something like that, but here the dark matter is exerting a force on something, then the dark matter will push things differently depending upon the amount of neutrons in that sample. Okay? So you can essentially search for this using what I would like to call a time-dependent equivalence principle violation search. Again, we'll see why that's useful shortly. There's another particle called the relaxion. This is a particle that I'm very happy about. Anyway, I won't go into the details of this stuff, but this is a new way to solve the hierarchy problem. Okay? And the basic idea of the relaxion is that there is going to be some new light particle that couples to the Higgs. Okay? And this is one of the other generic couplings that a light dark matter particle can have. Whether you believe the relaxion story or not, this is something you can look for. Okay? So there's a G phi Higgs square coupling here, and since the Higgs gives masses to all fundamental particles, once the Higgs has fallen into the web and acquired a web, and electroweak symmetry is broken, there is now an effective coupling between the relaxion and the masses of fundamental particles. So if this particle is a dark matter, there is going to be a time-varying field associated with it, and because it's in the galaxy, there's also velocity of this field. And so essentially, this is a coupling in the potential. You take its derivative, you realize there's going to be a force on atoms that is proportional to the gradient of this field. So as the dark matter flows through, it has a velocity, there's a gradient of this field. That gradient will give rise to a force on atoms. Okay? And once again, this is time varying because the field is oscillating. And because this is a force that is going to the Higgs, and the Higgs doesn't care about the equivalence principle, once again, this force will also violate the equivalence principle. Okay? So you once again realize that you've got a time-dependent equivalence principle violating force you can go look for. How can you find such a thing? You can actually leverage a lot of the work that has been going on these days to search for gravitational waves to do these things. Okay? And also a lot of the work that's gone on to search for equivalence principle violation. So here are a couple of experiments. The first is something you can use at the University of Washington. The Adelberger group has for years been doing pioneering and wonderful work on searching for equivalence principle violation with these so-called torsion balance experiments. What do? They have a titanium and a beryllium rod, and they're looking for the fact that if one of them is falling more than the other, the rod will bend. So what can happen here is that the dark matter is coming in. The dark matter is exerting a different force on titanium versus beryllium, okay, causing that thing to rotate. So you can basically ask, the dark matter is pushing differently on different ends of this titanium, on this torsion balance, and that gives rise to an angle that keeps changing, and you can measure that with an optical interferometer. There's another experiment going on at Stanford where what they're trying to do is basically dropping rubidium-85 and rubidium-87 in what is called an atom interferometer and trying to see if one of them falls faster than the other. They're trying to do Galileo's experiment, right? So once again, you drop these two guys and you see one of them is going to fall faster than the other, and the idea is that the dark matter could make that happen because it's going to exert a different force on these different things. And this experiment is now actually very recently been generously supported by the Gordon Moore Foundation. They gave them $10 million to do it. Okay? So what is the advantage of doing this experiment? Right? What is interesting about it? So if you normally just think about equivalence principle searches, there is a background that they have to face, which is the fact that we live on the Earth. Right? So let's say you're doing this experiment, this dark matter experiment on the Earth. This equivalence principle violation experiment on the Earth. You're dropping rubidium-85 and 87, and you're trying to see one of them will fall faster than the other. There's a big systematic in that you have to make sure that you drop these guys from the same point on the Earth. Because if you drop one of them slightly above the other, they will fall differently. At that point, what you have learned is not that you've discovered an equivalence principle violating effect. You've just discovered the fact that the Earth is a sphere, right? Because it's a gravity gradient. But if this thing is a dark matter experiment, even if you drop one of them slightly above the other, as they fall, the dark matter will exert a force at some time, which will cause one of them to fall faster than the other. But since the dark matter force is time varying, in the next time it will flip, right? So the fact that you have a time-dependent signal here makes it very easy to combat a lot of systematics. And that is a theme that is repeated throughout the story. It's much easier to see it here, but it's also true everywhere else, that how time dependence at specific frequencies can help you beat a lot of systematic background. Okay? And that is one of the reasons why it is possible to make significant advances in this story. It is also possible to look for these effects through something called pulsar timing arrays. These are actually existing experiments to look for low-frequency gravitational waves. And the idea is the following, that you have a bunch of pulsars. They're known to be incredibly stable clocks. The pulsar is just rotating, and that pulsar keeps sending signals towards us, and we are basically looking at the arrival time of the pulsar signals on the Earth. So what the pulsar timing clocks are looking at is the fact that as the gravitational wave goes by, the distance between us and the pulsar will change, and that modulation is what they look for. We can basically leverage their work to essentially look for dark matter as well because of the following fact. So think about something like the B minus L or something like that, right? So this dark matter will exert a force on a pulsar and on the Earth. The pulsar, of course, is dramatically different than the Earth. So there's an order 1 equivalence principle violating force that the pulsar is experiencing versus the Earth, which means the pulsar will move a little bit more than the Earth will, and thus that modulation you can pick up using the pulsar timing array. Furthermore, for particles like the relaxion, the mass of the electron itself will keep changing on the Earth. So the way you really do this experiment is that you have an atomic clock on the Earth, and you're basically asking the pulsar signal coming in repeatedly, and you're using the local clock to see, is there a change in the arrival time? But if the mass of the electron locally changes, the atomic clock will also wobble, and that is, again, something you can use to detect this effect. So there are a variety of possible ways to go a lot of orders of magnitude in this game. Pulsar timing arrays, atom interferometry, torsion balances, all kinds of stuff. The main thing I want to excite you about is basically, well, look at the huge amount of white space that one can actually probe in these kinds of experiments. Okay? So with that, let me switch gears sort of midway through the talk. Maybe I've gone a little bit more than midway, but hopefully not too much. And talk about the two other ideas that I wanted to discuss. One is, how do we go beyond WIMP dark matter, okay, to go beyond this sort of solar neutrino floor? How do you do that? What kind of ideas can we actually have to do that? And the second is basically, if you notice so far, I only talked about dark matter below a gigahertz or 100 gigahertz or so, right? So how do we actually search for dark matter with bosonic with mass above 100 gigahertz? What kind of ideas do you have to actually do that? Okay. And the basic point here is that if you think about it, the reason why the story worked very nicely at low frequency is because the coherence time of the signal was very long, right? If you notice, the coherence time of the signal was 1 over mv squared. So the lighter the mass of the particle, the more time the signal was going to remain coherent. And the more time I had to measure it, it becomes possible for me to measure a smaller and smaller phase, if you will. So like everything in the world requires time to build up. So if I have a signal that's coherent for a long time, I have more time to see it. And that's what made all of this possible. As you go to higher and higher mass, the coherence time gets very short, so I don't have enough time to build a signal. So how do you actually try to beat that? So that's going to be the remaining part of this talk. So let me start off with directional detection of dark matter with crystal defects. This is actually a proof of concept of this version of this work was funded by the Department of Energy through their quantum initiative stuff. And it's basically being, this proof of concept is being built by Misha Lukin and Ron Wadsworth at Harvard. So here is the main issue, right? So neutrinos and dark matter, WIMP dark matter, scatter in a very similar way, right? There is some detector material you have. The dark matter and the neutrino, for example, can come in. They hit an atom. They knock that atom from where it used to be, and the dark matter goes away, okay? So this is what you're trying to see in these experiments. So they look identical, and we live next to the sun, for good or bad. And the sun produces neutrinos, and there's an irreducible background to dark matter experiments, so for WIMP dark matter experiments, because in the next generation or so, these neutrinos will come and solar neutrinos will come and scatter in these experiments, and then it'll be hard for you to distinguish that event from that of dark matter. Okay. So one possibility is that you can make use of the fact that the dark matter is supposed to be isotropic, it's coming from all directions, while we know the location of the sun. And thus, if you had a way to tell which direction the particle came and scattered, you can then veto all events that point towards the sun, okay? And that will remove that background completely, while you will be open to the isotropic background that remains, okay? And that will be something that you can hope to do to make progress. The big challenge here is that you need a large target mass in order to be useful, because we're looking at very, very low cross sections, 10 to the minus 47 centimeters squared, 48 centimeters squared, which means you need a lot of mass to even be able to detect either the dark matter or the WIMP, to be in business. And then you need to thus be able to tell the direction in which something came in, okay, in a large target mass. And if you don't want to build an Earth-sized detector, basically you have to be able to do this at solid state density, right? So the challenge is basically I have a solid, the dark matter came in, it's scattered, okay, and there's some recoil in there. I need to know the direction at solid state densities. How is this possible? Let's first look at the physics, okay? What effects do we have, okay? And then we can talk about how to see it. What happens? Say the dark matter, the neutrino comes in, it scatters. It's going to knock that nucleus off its location. And that nucleus will basically get kicked out with something like 10 to 100 keV of energy, and it's going to move forward and do a bunch of damage, right? It's like taking a bullet and shooting it in a block. It goes in and does a bunch of damage. This is your bullet, it does a bunch of damage, okay? So if you look at it, what actually happens is that when you knock an atom off its position with, like, say 10 keV of energy, it goes around, it creates a bunch of damage in the lattice. And that damage, if you will, is well correlated with the direction of the initial recoil, okay? That's not surprising because of momentum. The whole challenge, though, is that this entire damage, okay, this little track that exists, is localized within something like 50 nanometers, okay? So if there is some way, okay, in which you could actually tell this damage, you'd be in business. And if you don't believe me, you can run a trim simulation and see exactly what happens. So roughly what you can do is that you can take like a 1 keV or 10 keV ion that you put into a system, like some kind of crystal, and you let that thing go forward and create a bunch of damage. And what you typically end up finding is basically that this ion creates something like 200 to 300 lattice vacancies and interstitials. And that kind of makes sense, basically because you put in something like 30 keV of energy. The amount of energy you need to kick something off the lattice is something like 30 eV or so. So with something like 10% efficiency, you're creating damages in the crystal, okay? That's what you end up getting. But to be able to see this damage, so this physics exists. It exists in a solid. I take the solid, dark matter comes and scatters. That damage does exist. But I need to have some kind of nanoscale measuring device to be able to tell what's actually going on. And that is where there's very interesting technology of what is called nitrogen vacancy centers in diamond. That's kind of interesting. So this is kind of cool technology, okay? So you take diamond, and you create lattice vacancies, okay? You create holes in it, and then you put a nitrogen next to it, okay? And if you remember your chemistry, this nitrogen has an unpaired electron next to it. And what you can do is that you can shine light at this diamond and excite this electron, okay? And that electron will move back and forth and emit light. So you can basically measure the spectrum of that electron. And it turns out that this spectrum of the electron is sensitive to what's going on near it. Okay? So as you can imagine, this is only a local sensor, but it's basically sensitive to the crystal environment at the 50 nanometer scale. Experimentally, people have in fact demonstrated the creation of these NV centers at very high density, 1 per 30 nanometer cube of NV centers in bulk diamond. So this is millimeter cube of diamond, not centimeters or meters or whatever. It's just millimeter cubes, but it's still, you know, a reasonable chunk of material where these high densities have been demonstrated, or these NV centers. And in fact, nanoscale measurements at this level have been demonstrated by many people around the world. Okay? So the idea is that you have this diamond, it has these vacancy centers, you shine light at it and try to see if something interesting is going on over there. So it's an interesting question to ask, that given that this technology has been independently developed, can it actually be used to tell the damage cascade on an NV center, right? So remember, the problem of directional detection was that there is a damage cluster that is nanometers in size, 50 nanometers in size, and I now have a sensor that is able to do nanoscale measurements. Can these two things be combined together? Now you might ask, okay, even if all of this works, who's going to give you a meter cube of diamond, right? So first of all, one doesn't need the kind of diamond that one gives one's spouse, okay? You can use like polycrystalline diamond, which is not as expensive. So it's roughly like a meter cube of it would cost something like 50 million. It's not nothing, but it's not insane. But at the same time, it's just very important to note that the similar kind of phenomenology, like everything I'm talking about, I'm saying the word diamond only because people study it a lot, but the same kind of idea where basically there is some crystal with some defect and I'm optically able to access that defect is also true in many other kinds of crystals. For example, sodium iodide has a famous F center, as it's called. It's a similar kind of thing. Okay, so you can also use other crystals to do this. It doesn't have to be diamond. But let's just ask a theory question. Okay, is it even possible? So what's going on? Okay, here's what we envisage, right? I have my crystal. I've created with these sort of large density of nitrogen vacancy centers. The dark matter comes in, it scatters, it does a bunch of damage. Okay? And remember, I'm creating something like 200 to 300 lattice vacancies. What happens? These atoms are now no longer what they're supposed to be. They have sagged, they're kicked around. And basically, when they get pushed around, they create strain in the crystal. Okay? So you can basically use Hooke's law to estimate how that strain dies off. I literally had to look up a paper from 1928 to calculate this. Okay? That's a strain, how it drops off from a single lattice vacancy. You get to multiply that by 100 to 300 because you have that many vacancies. And because of that strain, the NV centers levels will shift, right? Because there's a local strain in that system that will shift the levels of what's going on over here. So if you calculate how big that is, you realize that the shift in the NV centers line is something like 100 kilohertz or so at 30 nanometers away from the damage, while the natural line width of that thing is something like a kilohertz or so. So what you realize is that a single NV center has sensitivity to this cascade. Not only that, the signal to noise ratio locally is very big, it's 100, right? It's not too surprising because I have a very low density of NV centers, 1 per 30 nanometer cube. The dark matter comes in, it does a bunch of damage, and within that small region, I've created like 100, 200 vacancies. So locally, there's a huge signal to noise. The challenge, of course, is that this local thing exists in a big, gigantic bulk. So how do I localize and find it out? Right? So it's a very much a needle in a haystack problem, where when you hit the needle, you're goddamn sure it's a needle, but you got to find the needle. So here's a detector concept of how we envisage something like this could work. We're going to basically imagine creating this a section detector, if you will, where we will basically have, let's say, a millimeter thickness, but maybe like a meter squared area style thing. Okay, eventually. Okay, some crystal of this sort is sectioned in this way, where it's like in plates put together. The thickness is all that really matters in the story so much. And we're going to imagine we're going to start that out by creating these large density of NV centers in there. Okay, so far only a millimeter cube has been demonstrated, but it's not crazy to think this is possible. And what we're going to do is we're going to use conventional WIMP detection ideas. We don't want to reinvent the wheel here. Use standard ideas that people use in WIMP detection, for example, using scintillation, ionization detectors, to identify interesting events. Right? So a typical detector will have a lot of events over the year. Most of them will be background. The WIMP guys know how to get rid of this. So they'll be like, okay, there are 10 events in the year that could be due to dark matter or neutrinos. Right? So basically, you identify there are 10 possible events, and they occurred, let's say, within something like a millimeter cube. Okay? That's roughly what you can know with current technology. So you basically say there's a millimeter cube here, there's a millimeter cube here, there's a millimeter cube here, where something interesting happened. Okay? So I've already localized with conventional ideas that in this big detector, in these few millimeter cubes, 10-ish of those, something interesting is going on. So you just pull out those particular parts of the segment, okay? And then you're going to use other techniques to localize it within that. So conventional ideas will localize within a millimeter cube. And then what you can do is essentially attain micron scale localization, okay, simply by shining light on that system. So there will be some part of that system where there is essentially something funny happened. You shine light. And within a micron, you can say, something interesting happened over there. Okay? And now you want to get to nanoscale resolution. That is, of course, hard to do if you have just a micron light, right? Because that's below the light's wavelength. And that's why really we have to section the detector, because what you can do to get sub-micron resolution is apply a big magnetic field on that little segment that will then shift each of these NV centers appropriately because of the magnetic coupling. And then you can access each individual sensor separately. And that's been experimentally demonstrated as well. Okay? So nanoscale resolution is possible. So that's the basic idea, right? You section the detector, you localize through crude methods where roughly something interesting happened, and then you're looking at 10-ish events, and now since that's a permanent kind of damage, you can spend a day studying each of those little samples and trying to see if something interesting happened or not. That's basically how we hope to solve the needle in the haystack problem. Okay? So I'll kind of quickly go through this. The basic idea is that if you run a bunch of simulations, it does look like, with a few events, we should be able to have 5 sigma efficiency if everything works to plan. And what Ron Woolsworth and company are doing now at Harvard is that they're trying to take some millimeter cube of diamond, shooting some neutrons at it, and trying to see if you can see what damage actually occurred there. Right? That's the idea. Then the final part of my talk is about these magnetic bubble chambers that I promised. And this is basically work done in collaboration with these guys. Giorgio, many of you may know, and Rupak, many of you may know. These guys are physicists, while Phil Bunting, Michael Nippe, and Jeffrey Long are chemists. And Tom is a former postdoc of mine who's now faculty at IPMU in Japan. So this is going back to this particular area, okay? How can we search for light dark matter above 10 to the minus 4 eV, okay? 100 gigahertz all the way to maybe even to a GeV. At that point, it's kind of heavyish dark matter. How do you do this? What is hard about this region? What is hard about the region is the following thing. I can't use the ideas that I used to detect very, very light dark matter because all of those ideas were leveraging the fact that there's a lot of time to do a measurement. At high mass, there's a lot less time to do that. And why can I use standard ideas that I can use to go after WIMPs is because dark matter that is light has very little energy. So it doesn't deposit much energy to be able to see in conventional calorimeters. So in my view, one possible way forward is if you had some way to amplify the deposited energy, okay? Say from, you deposit something tiny, you amplify it in some way, and that is something you could try to look for. The challenge of the story, of course, is that you need a large target mass. You're looking for a dark matter experiment, so you need a lot of mass. And you're searching for a very rare event, right? One event or whatever. So basically, you require an amplifier whose stability is very big, very long. If you have an amplifier that can amplify a tiny signal, but its dark current is like a second or something like that, who cares, right? Because you don't have much time to actually look for the dark matter that way. So here is the concept, okay? And strangely, this concept actually works. We have a demonstration of it even. So here's an idea. Let me take a spin. So let me take a system with a bunch of spins, okay? And so just a magnet with all spins aligned. And now let me apply a magnetic field in the opposite direction. That means each spin is now in an excited metastable state with energy g mu b, okay? And say the dark matter comes in, it collides, it deposits some heat. And maybe that heat causes that spin to flip. When that spin flips, it releases a stored Zeeman energy, and perhaps that energy can cause nearby spins to also flip, okay, leading to what we would call a magnetic deflagration or a burning of the material. So all these spins are aligned in this way, apply some heat, some spins flip, that release energy causes nearby spins to also flip. That would be a nice amplifier, okay? So this is the picture for it. Few spins flip and suddenly everything starts flipping. And that amplifies the deposit energy. It's a lot like a bubble chamber. That's why I call it a magnetic bubble chamber. The question is this crazy thing possible? Will this thing be stable? That kind of stuff. So let's understand why such a thing may even be possible. Okay? So this is what I want to do. I want to flip some spins and cause that to cause everything else to flip. This does not happen in a ferromagnet. In a ferromagnet, the spins are very close to each other, they're strongly coupled. So when one spin flips, it doesn't cause the nearby guys to flip. It wants to go back to what it was. It does not happen. So you require weak spin-spin coupling. So you might think, why don't you use a gas, right? Gases have weak spin-spin coupling. There's a big distance between them. But you can't do that because you need to have good heat conduction, right? When one spin flips and releases the heat, it has to go and hit the other guy and cause that guy to flip as well. So you can't use a gas. What you can use is you can use chemistry and do something called an organometallic complex. Okay? So what's an organometallic complex? I really have no idea. This is what it looks like. Okay? The basic idea is that there is a central metal complex, it's like manganese or iron, something like this, and surrounding that is a bunch of organic material, like an acetate. Okay? And this now does what you wanted to do, which is that there is now weak coupling between nearby spins because they're somewhat far from each other. Okay? And remember, the magnetic interaction drives us 1 over r cubed, so you don't have to go very far before the coupling becomes weak. So there's weak spin-spin coupling. At the same time, there's efficient heat conduction because the organic material can carry the heat. So this thing has all the properties you want to achieve this crazy thing. And this material gets a name. It's called a single molecular magnet, the idea being that each of these guys acts like its own magnet, right? And this is a recently discovered system in chemistry. The chemists are very excited. There are several hundred known examples of this stuff, and one can in fact make rather large samples of these guys. I'm told by even buying things on Amazon Prime. And this crazy thing, okay, this magnetic deflagration where you just cause some spins to flip through heat and the thing spreads, has been experimentally demonstrated in one well-studied example called manganese acetate, and also a few others. So this is experimentally true. No. The relaxation gets quick enough. The relaxation gets quick enough, right? Because basically, this stuff doesn't have like the nice symmetries that things normally have. So you're going from like one organic complex to the next. There's enough scattering that it just sort of goes up. It was very pure, yes. Yeah, but here there's a lot of local scattering. So what is the physics behind this whole process? It turns out you can describe this by a two-level Hamiltonian. Okay. So essentially, when there's no magnetic field, there's spin up and spin down, they have the same energy. When you have a magnetic field, there's one of them goes above the other. And the important thing is that there's a barrier between the two of them. That's the chemistry of the system. Okay. So when you have a magnetic field, the metastable state can decay to the ground state, but it has to go through this tunneling barrier. Okay. So the relaxation, the time it takes for this excited state to decay to the ground state, is given by some law like this, Arrhenius law, if you know chemistry, but it's just simple physics. And there's some relaxation time, tau naught, e to the u effective, which is some barrier stuff divided by the temperature. What you see now is something very interesting. This is a system that is very, very long-lived at low temperature, okay? Because there's some exponential stability. Fine, there's also some power law stability eventually. But you can see that at low temperature, the system can be very, very stable. But when you heat it locally, this localized heat, this barrier drops and you can quickly tunnel and decay. Okay? That's the main idea. So you have to ask, what sets the threshold? How much energy do I need before this thing actually goes off? This is a competition between two competing effects. So when you heat up a small part of the sample, the heat can diffuse out. That lowers the temperature. Or the spin can flip. If the spin flips, it releases energy, releasing more heat, which will cause the system to burn. The key point is that the heat diffusion scales as lambda squared, where lambda is a size that you heated it up to. Okay? So if you take a sample and you heat up a part of it of length lambda, the amount of time it takes for heat to dissipate there is lambda squared, because it's a random walk. Right? Turkeys take a lot more time to cook than small pieces of chicken for this reason. So the heat diffusion scales with the size over which you heated it up, while the relaxation doesn't care about the size at all. It's intrinsically set by these barriers. So in any system, if you heat up a sufficiently big sample, the spins will flip. Okay? So you can basically think of these parameters, U effective and tau naught, etc., as quantities that set the threshold of the detector. Right? Because if it's a system where the relaxation time is sufficiently short with a sufficiently small barrier, even a small amount of heat before it diffuses out will set it off. Okay? So you can get a low threshold detector. So if you look at the known examples, the gigantic list of these things, there are plenty of these systems with properties like low enough relaxation times and low enough barriers that in principle you can even get something like 10 millieV threshold. So all you need is 10 millieV in the system and the spins will relax. Okay? But we've not yet worked with those particular samples. We're just working with something else right now. That's the theory concept. The first thing you want to ask is it stable? What about backgrounds? Right? That's the main thing. What about backgrounds? What do you have thoughts about? Okay? So if you think about it, it's an interesting problem. Right? There will be plenty of high energy MEV things happening, radioactive stuff going on all the time. Okay? I asked the chemists about radioactivity and they were like, what radioactivity? We have no radioactivity in our systems. Right? They're not used to the incredibly low levels that the dark matter people have to deal with. Okay? So there will be MEV events happening all the time. We don't need anything fancy to say something happened in the MEV, right? There'll be enough heat and light scintillation or charge being produced that you can use conventional ways to realize something occurred at the MEV range, like an alpha particle went off, right? So the events at capital MEV are not a problem, okay? The problem is really the fact that the real background is essentially the fact that some radioactive thing has to give rise to a very, very low energy deposition. And that is really can only happen in a Compton tail, right? I must have something go off and that has to deposit like very tiny amounts of energy in the system. That can happen, but that's a Compton effect, right? A very forward scattering Compton. And what CDMS has seen is that this in fact is true. So at low energy, okay, the actual background, by which I mean the actual radioactive background that deposits tiny amounts of energy, is decreasing. Okay? So that's good. But these high energy events, radioactive events, are a problem in the sense that if they go off, even though I can identify something interesting happened there, that it was a radioactive background, if they keep happening too much, this detector will just be going off all the time, and I won't have a way to see the dark matter because this bubble chamber is constantly just flipping. Okay? So what you want is basically a way in which when the detector goes off, I don't lose too much operation time. Okay? And that's kind of a big problem for bubble chambers because these bubbles go off, they have to recharge them again, start up again, do all these things. Here's an interesting fact about these particular systems is that let's say you start with these systems, all these things, there's a spin like this, a magnetic field opposite like that, and now I'm going to put a squid next to it. Okay? With the precision magnetometer, I don't need the entire crystal spin to flip to know something happened. Right? Basically, once this flame gets shut off, if I have a fancy squid, within something like 10 microseconds, I can figure out something interesting happened. At which point, I can simply turn off the magnetic field. If I turn off the magnetic field, the fuel in the system is gone. The flame stops. Right? So what you will do is that every time a background happens, I turn off the magnetic field, the flame burns a 10 micron size sample of the system. So okay, you lost some amount of detector volume, but who cares? You still have your operation time. So that is one way to handle this problem. Another way to do this is also to actually just use, instead of a big crystal, it's much easier to make powders of these things. Like, they're sort of a 10 micron size powders of these things. You just lump them together, in which case the heat will just, you burn like a 10 micron size bit of the powder. Who cares? You can see it happen with the squid, but it's not a background anymore because it doesn't spread to the rest of the system. So we have some potential reach for what we can do out here. And it's interesting that you can actually cover a lot of territory, okay, or a lot of parameter space in this particular thing. So let me show you the results of a trial that we are doing. So Rupak Mahapatra actually built this thing in Texas A&M. So here's what they did. They used manganese acetate. So this is the example that everyone has well studied. So it ought to work there. And here's the setup. Okay, here's a sample, which is this spin that we have, and then we put some radioactive source next to it. Okay, in fact, we had two sets of these things. One, there's a sample and a source. The second one only had a sample and no source. And then what you do is you have a Hall sensor to see if some interesting magnetic field effects are actually happening on in there. And so the source was a microcurie americium-241 alpha source. The other one had no source at all. And then you can ask what happened in the system. Here's what we observed. So this is the magnetic field of that sample. And what you're seeing is basically that the red one is the one where there's a source. And clearly you can tell that there was a time when something happened to it, but the magnetic field jumped significantly. Okay? While this is the blue thing, which is something where there is no source at all, and the magnetic field is just constant, more or less, with an error. Right? So this is pretty convincing evidence that this detector idea makes sense, that I can actually have heat deposited from a radioactive source that sets off this crystal. That is something you can actually measure, while when there is no such thing happening, nothing interesting happens. So it's stable over that period. How excited should you be? Not terribly, because manganese acetate is a system that has a very high threshold. Its relaxation properties are pretty bad. So effectively, it needs a few MeV, capital MeV of energy to set it off. Okay? But that's something we can calculate. So all this thing, in fact, shows is the fact that my very boneheaded, theory calculation of doing an order of magnitude estimate sort of makes sense. Our plan now is to actually go beyond manganese acetate, since we've demonstrated it sort of makes sense, to a couple of other compounds which are in the ion category, and those guys have KeV thresholds. So that's the next step in this process. So I'm definitely out of time, so I'm going to conclude. So my main motivation over the last several years has been that given this enormous range of masses of dark matter could be, it is silly of us to be focused on just any one of these parameters. We should just go out and look for all. And obviously, if every one of these experiments costed 30 people years and billions of dollars, we can't do and search all of these things. It's not possible. But that's not the case, right? Each of these experiments that are covering a bunch of territory are, maybe tens of people, like maybe a couple of PI. I'm just talking about actual people, not PIs. So maybe like tens of people getting together, several $1 million, are able to put together some experiment that makes sense and able to probe a lot of parameter space. And I really believe that's necessary for dark matter, right? Because I'm not just saying it because I've been working on it, but really this is a fact. There's a huge parameter space. Let's go look everywhere. Thank you. Yeah, exactly. So basically, you have, let's say, one NV center per 30 nanometer cube. So you have like a grid of these NV centers. And basically, this thing is coming in. It's going to create a damage trail. And the strain depends upon the direction of that damage trail. So you, let's say, look at all the NV centers around that grid, 6 of them or something like that. And depending upon what each of those measure, you can basically say whether the tail went like that or whatever. Yeah, so we did a simulation of that, and basically what we can do, I mean, that's something that I skipped over very quickly, was the fact that with something like a pretty low false positive rate and an efficiency of something like 80%, we were able to tell the direction in the simulation. You can. So yeah, that's exactly my point. You can actually use other things as well. It's just that the NV center is something that these guys are well studied. Right. It's what? Yeah, it's just the fact that yeah, so in a sense, like basically, right. That is correct, because now you essentially have a cycling transition that runs many, many times, and thus you're able to measure that state more easily. That plays a factor, yeah. No. Yeah, you should see it's there or not, absolutely. Yeah. Yeah. Okay. Thank you.